Hello again, physics friends. I'm thrilled to be talking to you today about classical mechanics overview and context. I just want to kind of set the stage of where classical mechanics fits in with your broader physics experience. And if you have had experience with special relativity and or quantum mechanics, perhaps in Physics 100 or elsewhere, this will make additional sense to you as well. You'll know the contrast between classical and quantum and relativity quite clearly. So let's get started. I mean, one of the things I want to make sure we're clear on is what are the assumptions that we're going to be making when we start talking about classical mechanics in this course. And one of the first things that we're going to have to assume, or we will assume, is this idea of measurement. We're going to basically assume that we will be able to measure the position and times of occurrence of events with arbitrary accuracy, right? And so we can kind of represent that graphically here. If we have a coordinate system, then in that coordinate system, we might have an event, say this blue dot, and there's some coordinate associated with that event. So we could identify an X, Y, and Z coordinate. So this event might be happening at some position in space and some position in time as well. So we could represent the X, Y, and Z coordinates with just the Cartesian coordinates X, Y, and Z. And additionally, we're going to assume that we know exactly when this event occurs. So we'll call that an event. Okay, and if you've worked in the context of special relativity, you understand the deep importance of this idea of an event. In the context of our class of mechanics, we're just going to talk about the position of an object and the time that it's at that position. We can think of those as events. And here we're assuming that we have arbitrary accuracy with which we can measure the position and the time of any given event. Additionally, we're going to assume that we can measure with arbitrary accuracy the velocity or momentum of a particle. And that is very different than what you know is true in quantum mechanics. So I'll put in here, I'll just write quantum as a way for us to remember this is a difference between classical and quantum. We also are going to assume that we have reference frames to begin with. We've kind of implicitly made this assumption because we've already written down and drawn a reference frame and talked about a specific time. But we're going to say, just for clarity, we're going to define a reference frame as an observer with clocks and sticks. So a way to measure time and a way to measure length. And that's going to define our reference frame with some origin. We are also going to assume simultaneity. By that, what do we mean? Well, we measured some event and we labeled it X, Y, Z, and T. And let's say another observer observes the same event. They might label it X prime, Y prime, Z prime, and T prime. Although their space coordinates, X, Y, and Z prime, may differ from ours, X, Y, and Z unprimed, their time coordinate is going to agree with ours. All observers are going to agree on time in classical mechanics. Of course, that breaks down in relativity, where we learn that time is relative and depends on your frame of reference, but for our work, we're going to assume simultaneity. Much like you will have seen in your previous mechanics courses, we are also going to talk about so-called point particles. These are, or point masses. These are idealized objects that have a finite mass, non-zero mass, but that have no size. They don't take up any space. And one of the powerful things in mechanics is, whether this object is a brownie or a baseball or a bell, its trajectory in many cases is independent of its shape or composition, and sometimes even independent of its mass. So in situations where the kind of dressing on the object, the shape or the color or so on, doesn't matter, we'll abstract that away and just talk about the point mass for simplicity. The final topic I want to make sure we cover here is that of inertial frames versus non-inertial frames. So not all reference frames are equivalent. The equations of motion can look different depending on your frame of reference. And in particular, they would look different in an inertial frame versus a non-inertial frame, also called an accelerated frame. So I want to take a little time to talk about inertial frames and make sure we're all on the same page here. In this class, we're going to focus on inertial frames and motion in inertial frames. So we better understand what makes an inertial frame inertial and how to tell if you're in one or not. So here's a practical way to think about what an inertial frame is versus a non-inertial frame. So let's, for example, compare a person who's at rest on the surface of the Earth with a person in a car that's making a sharp right-hand turn. And let's see what that person would say in each of those two cases if they just release a ball and watch it fall. Okay. Well, a person at rest on the surface of the Earth would say something like the object falls straight down due to gravity. Whereas the person in the car will say, no, the object falls down and to the right. Now, it falls down because of gravity. Why does it fall to the right? Well, of course, we know there's not actually a force pushing the ball to the right. It's an effect of observing the ball falling in a non-inertial frame. Now, there's not just one reference frame in which the ball falls straight down. There's, in fact, an infinite number or a family of such reference frames. And in those reference frames, we say the ball falls straight down, and equivalently, the equations of motion are the most simple, and indeed, we are going to call those inertial frames of reference. Newton's laws of motion that you're familiar with are all built with an assumption of an inertial frame. In fact, Newton's first law is essentially a definition of inertial frames. We can frame it in the following way. We say Newton's first law says, in an inertial frame, an object experiencing no forces will move in a straight line at constant speed, understanding that that speed can be zero. In other words, the object could be at rest. So by way of closing, I want to say a few words about inertial frames. The first is that a true inertial frame really is an idealization. In practice, all that matters, though, is that we can ignore non-inertial forces if they're small compared to the effects we're studying. So here's an example. The surface of the Earth, is that an inertial frame? Well, technically, it's not an inertial frame. The Earth is rotating. If you're standing on the surface of the Earth, you are in a rotating frame, which is definitely a non-inertial frame. But does that matter in practice? Well, one way to see if it matters is to compute the acceleration due to the motion of your frame relative to an inertial frame and see if that acceleration is large compared to other ones that you care about. So we can do that in the following way. We can say for the Earth, the Earth rotates at a rate capital omega, which is something like 7 times 10 to the minus 5 radians per second. That's 24 hours per revolution. Okay. And let's say that we are curious about the trajectory of a baseball. Okay, so if you throw a baseball, the velocity of the baseball might be something like 50 meters per second or so. And there's an acceleration associated with that motion, which depends on the cross product of the velocity of the ball and the Earth's rotation. Okay. So we don't have to work out all the details here, but we can just approximate this as 2 times the magnitude of v times the magnitude of omega. That's kind of the maximum that this acceleration could be. And when you put in the numbers, you find something like 7 times 10 to the minus 4 meters per second squared. Okay, so there's going to be an apparent acceleration from this non-inertial fictitious force that's on the order of 10 to the minus 3 meters per second squared. And you want to compare that with other accelerations in the problem. Okay, so the most important other acceleration is that due to gravity, which near the surface of the Earth is about 10 meters per second squared. So in that case, this so-called Coriolis force, or the Coriolis acceleration, is negligible, right? So the Coriolis acceleration is much, much smaller than the gravitational acceleration. And so when, if we're talking about the trajectory of a baseball, we do not have to worry about the fact that we're throwing the baseball from a rotating or non-inertial frame. We can treat the Earth as an inertial frame. If, however, you are studying the dynamics of hurricanes, in that case, the Coriolis force becomes very important. Okay. Also, even if you ignored the rotation of the Earth, don't forget that the Earth is also in orbit around the Sun, and the Sun is in orbit around the galaxy. And in particular, we know it takes about 1 year per rotation. Well, it takes 1 year per rotation about the Sun. So that has an angular rotation rate of 10 to the minus 7 radians per second. And it takes about 220 million years for the Earth and Sun to orbit the center of the galaxy, which gives us this even smaller angular acceleration. So even if you ignored the rotation of the Earth, be aware that the point-like Earth would be in a non-inertial frame technically, although do we need to worry about these when we actually do calculations? Probably not, unless the accelerations of the other accelerations in the problem were small compared to the resulting fictitious accelerations associated with these angular rotation rates. The final thing I want to say is, okay, let's say you know that you're in a frame and it's inertial. How do I find other frames that are also inertial? Okay. So we can write this down actually mathematically, talk about how you relate one frame of reference to another. And we can do it in the following way. So let's imagine two reference frames, call it S and S prime, and we'll let them be in relative motion with respect to each other at velocity v, so that the position vector of an object in S prime is equal to the position vector in reference frame S plus this other vt term. So what that means is that t equals 0 in this formulation, the two reference frames coincide, but as t evolves, the two reference frames start to separate. Well, in that case, if we have a particle that's moving with a constant velocity, let's call it u, in the reference frame S, then the position of that particle will be whatever it starts at plus the vector u times t. Okay, so we have a particle that's moving linearly at constant velocity in frame S. Well, what does that look like in frame S prime? Okay. Well, we can say that we know that any position in the primed frame is going to be equal to the position in the unprimed frame plus vt, which is the relative velocity of these two frames. But we also know that in this case, the position vector r of t is given by the equation above for this particular particle. So we can write this out as r naught plus ut plus vt, okay, where the first two terms are coming from the motion that we know about in frame S, and the second term, this third term rather, vt, is how the two frames are related to each other. But these second and third terms are both some velocity vector times time. So we can factor out the time there, and we see the following. That the position vector in the primed frame for all time is equal to a constant, which is the starting position, plus a new velocity times time. So we can combine u and v, and we can call it something else, w. And what we see is that the description of the position as a function of time in the primed frame is also linear motion at a constant velocity, right? So w is also a constant velocity. Constant velocity because it's created by summing together two other constant velocities. So the motion in S prime in the second frame is also linear at constant velocity, just as it was in the first frame. So what we learn now is that if S was an inertial frame, then so is S prime. Okay, and that's true as long as S and S prime are in relative velocity, a relative motion by a constant velocity. So here's our main conclusion. We can now say any frame of reference, all frames of reference that are moving at constant velocity relative to a known inertial frame must also be inertial frames. Okay, so here's one way to find an inertial frame. Find a frame in which an object is at rest and it's experiencing no force. Okay, if the object is at rest and it's experiencing no force and it continues to be at rest, then that frame is an inertial frame. And any other frame of reference moving at a constant velocity relative to the first frame is also an inertial frame. Okay. So what we've done so far is just given a very brief overview of all of the kind of underlying assumptions that go into classical mechanics. And in particular, we've really taken care to define what an inertial frame is and how you know if you're in one, and if you're in one, how to find another one. And this is all to highlight the fact that the work we'll do this semester will assume, unless otherwise stated, will assume that we are working in an inertial frame. And in particular, Newton's laws as originally posed assume that you're living in an inertial frame and working in an inertial frame, like F equals ma, where F net is all of the net real forces acting on an object. That's true if you are in an inertial frame, and so on. Okay, so with that, we'll wrap for right now, and next we'll get back to Newton's laws and solving for the motion of particles in inertial frames. And until then, take care and be well.